Hello everyone, NeuralNar here, and today we're going to talk about total harmonic distortion. And to help me out in front of me I have 4 inverters on the table. The 2 on the left are sine wave inverters, pure sine wave, or at least they're advertised as such. And the 2 on this side are modified sine wave inverters. I have a low priced unit from each type and a good quality one from each type. Ames power I would not recommend, but it is a higher priced inverter, so I'll just call it a higher quality one. This here is an USP Tiger Claw 1500 watt inverter. I had done a review on this earlier. If you're interested in that, go ahead and check it out. I was actually pretty impressed with its performance. This back here is an Ames Power 2000 watt pure sine wave inverter. I'm not at all impressed with that. I would not recommend that to anybody. I don't have a review on it. And over here I have 2 modified sine wave inverters. This one is a Whistler 1600 watt power inverter. And back here is one of my favorites. This is a MotoMaster 3000 watt inverter. It's actually a Xantrex X-Power inverter, an old design, but it's one of the most efficient inverters I have, and a pretty clean output waveform as far as modified sine wave inverters go. So these are the 4 that I'm going to be using for this demonstration, and specifically we are going to be talking about these 2 because these are the pure sine wave inverters. The one in front is rated for 2% total harmonic distortion. If that's true, it's pretty impressive. I have my doubts. This one back here is rated for 3% total harmonic distortion. Now, what is total harmonic distortion? If you're not familiar with that, basically it's a measure of how clean the output waveform of an inverter is. If this is rated for 2% THD, total harmonic distortion, that means that 98% of the output power is coming out at 60 Hz. And the other 2% of the power is coming out at some frequency other than 60 Hz. Maybe it's 120, maybe it's 180, maybe it's 240, maybe it's 200 kilohertz. Who knows? But it's some frequency other than 60 Hz. This one back here is rated for 3%. Now, another question might be, well, why do I care? Well, for some loads you may not care. For example, an incandescent light bulb, it doesn't really care. It has one job and one job only, and that is to get hot. Same thing with your coffee pot, it probably doesn't care. But there are lots of loads that do mind. Anything with a motor, anything with a transformer, anything with a capacitor is going to care a lot about the quality of the output waveform. For example, refrigerators, microwave ovens, air conditioners, fans, all of those things do care about the output waveform because, for the most part, they can only use the portion of the power that is 60 Hz. The rest of the power just ends up getting wasted in one of 2 ways. For a fan, for example, it may draw about the same amount of power from your inverter, no matter if it's a clean output waveform or not, but it'll turn slower and might make a buzzing noise, for example. So it won't blow as much air for the same amount of power input. It won't work as well. Other things like refrigerators, they may run okay, but they'll take more power because they can only use the portion of the power that is at 60 Hz. The rest of it is wasted. Anyway, before I bore everybody to death, let's get started on the testing here. To take a look at the output waveform of them, I have this Fluke 41 power analyzer. I'm going to hook that up to each of these one at a time, and we are going to take a look and see if they match their advertising specifications. Specifically, these 2 here. Now, these 2 inverters over here, these are modified sine wave inverters, and they never rate these for harmonic distortion. And the reason for that is because modified sine wave inverters are ungodly bad in terms of distortion. They're usually between 25 and 50% total harmonic distortion, meaning that you could have as little as 1/2 of your power being useful. I'll make another video on this later, specifically talking about the efficiency aspects of it, but for now we're just going to take a look at the output waveform, and even more specifically, these are the 2 I'm interested in. Do they live up to their advertising specifications or do they not? And we are going to be using these 2, a very cheap inverter and a slightly better one, just to do kind of a comparison, to see how these compare to these. We're all set up and ready for the first inverter, the USP Tiger Claw, and this is my test setup. I have a standard 100 amp hour deep cycle battery over here. It is in very good condition and fully charged. I'm just going to use this setup for everything, use the same battery hooked up the same way. That way, that's all the same. To do this test properly, I'd have to test all of the corner cases, high and low battery voltage, hot and cold temperatures, high and low loads, capacitive, inductive, resistive, all those combinations, etc., etc. It would take a long time. I don't think anybody really cares, so I'm just going to do it this way. They're all going to be hooked up to this one battery, and I'm going to test 3 different loads. One of them is no load. We'll see how clean the output waveform is at no load. Another one is just a resistive load. I'm going to load this thing down to about 1500 watts, since they can all handle that. And we'll see how clean the output waveform is at full load, or at least a heavy load. And third, I have my full-size refrigerator that this extension cord over here is running out to. It takes about 150 watts or so to run that refrigerator. It's a modern refrigerator, but it is a full-sized one, so we'll see how it does on an inductive load. And this is my harmonic power analyzer. I have that hooked up in the safest way humanly possible. Yeah, don't comment. And I'll turn that on and we'll get started testing here. Alright, I think I have this in a place where we can both see it. I have the inverter, it is on, and it is not under any load. I'll turn on the analyzer and we'll see what it says. So we have about 119 volts out and 3.3% total harmonic distortion. Well, already this inverter does not live up to its specification of 2%, and that's under no load. This will probably get worse as we put it under load. Switch that to the waveform, and that is the voltage waveform. I don't know if you can see it on the camera or not, but there's a little bit of dead time right around the zero crossover, and that's pretty typical of an inverter. I'm not going to fault this one for that, but that is something to note. And this is a graph of which harmonics are showing up in the waveform. You can see that we have 2.5% of the voltage is the third harmonic, 0.7% is the fifth, and these are all pretty low, but some of these do exist. Go back to the original screen here, and now I'm going to turn on this full load 1500 watts. And that is a purely resistive load, an electric heater. You can see that the output voltage sagged quite a bit on this, 206 volts. This inverter, even though it's rated for 1500 watts, really can't power 1500 watts properly. In any case, what we care about here for this video is 5.2% distortion. It is definitely getting worse under load. If I switch to the graph, you can see why. There's a flat bottom and a flat top on the waveform. That's what's causing our distortion. And if I go back to the graph, you can see that this one got a little bit bigger. There's now more harmonic content at these higher frequencies. These numbers at the bottom are the harmonics. 1 stands for the first harmonic, 60 Hertz. 2 is the second harmonic, 120 Hertz. 3 is the third, 180 Hertz. And so on up the line. This particular meter only goes to the 31st harmonic. But once you get up that high, there's not much left anyway. Another thing that's interesting is this screen right here, which shows the voltage versus current draw. This straight line means that it is a purely resistive load. The more voltage you provide it, the more current it takes, and this is the opposite side of your waveform. The more negative it is, the more current it takes in the negative direction, but it is a straight line. The fans in it just turned on, so I'll probably have to speak up a little bit, but I just turned my heater off, and now you can see this line is just a horizontal line. There's no load on it anymore. And now I'm going to plug in my refrigerator. So this is that same graph showing the voltage versus current, and you can see now that there is a loop. That is hysteresis. This load is partially inductive, the refrigerator. It's a PSC motor in the refrigerator, so there's some capacitive component too, but I'll just call it inductive because it's a motor, and that's what that loop means, that there's some inductance to it. I won't show this again, but for some of you that are a little bit more technical, I thought that might be interesting. So I'll go back to the actual readout here, and now you can see that it is at 2.5% total harmonic distortion. So this inverter really is pretty respectable. For the price point that this one is sold at, you can easily buy it for $200 after shipping. I got this for even less. The output waveform is pretty clean, has a good surge capacity. and it really works pretty well. I'm quite impressed with this inverter. There's the waveform, nice and clean again. It'll also give you the waveform of the current, which is not of interest for this video necessarily, but I'll just show it anyway. You can see that the current draw of this refrigerator is not a clean wave. That's to be expected. That's not the inverter's fault, that's the refrigerator doing that. And there's the wattage load. Just for anybody who's interested, I'll show these screens. You can skip over them if you don't really care. Power factor of 0.95. So this refrigerator is drawing 128 watts right now with a very high power factor, 0.95, because it is getting a sine wave input and 134 volt amps. But again, before I bore everybody too much, that is the USP Tiger Claw. The total harmonic distortion is typically between 2 and 5%. It does not meet their 2% specifications, but it isn't too bad. It's a pretty clean output waveform. Now this testing does not show the radiated emissions, meaning interference for television, radio, that sort of thing. The Whistler inverter that I'm going to be showing later is actually so bad for radiated emissions that this camera that you're looking through right now, the audio of the camera actually gets a little bit messed up if you get too close to it. So that's kind of a concern. It might be mistaken for a landing beacon and I'll have jumbo jets trying to land in my backyard or something. The rest of them don't do that. I'm not measuring that. I don't have the equipment here for that. I have access to it, but it's really not of interest to anybody. So I'm just going to be covering the harmonic distortion readout. So this is the USP Tiger Claw 1500, and now we're going to be moving to the Ames Power 2000 watt inverter. It is about twice as expensive as this one, and we'll see if you get anything for your money or not. Now we move on to the Ames Power sine wave inverter. I have the inverter on, and I'll turn on the analyzer. And you can see that it too is about 119 volts. And the distortion at no load is about 2%. There's the waveform. It looks pretty good. There's still a little bit of dead time there around the zero crossover, but this is a little bit cleaner than the USP Tiger Claw. They're both respectable though. And here is the harmonic content. It's also a little bit cleaner. So now I'll turn on a 1500 watt load and we'll see what it does. The first thing I want you to notice is that this is a 2000 watt inverter. With a 1500 watt load, it's sagged to 107 volts. This can't do 2000 watts. I don't know how they advertise it that way. It can't even do 1500. So basically they're just lying to the customers, but that's not what this video is about. So 107 volts, but the total harmonic distortion is 3.7%. They advertise 3% for this inverter, so that's not true, but it is pretty respectable at 3.7%. I can't really knock it for that. If we go to the waveform still looks pretty good. You can see that the top and the bottom are still pretty much a sine wave. It's not clipping like the other inverter did with this load. And this is the bar graph. It looks like most of the distortion in this inverter happens at the higher frequencies, whereas with the USP Tiger Claw, the distortion was at the lower frequencies with the top being clipped off of the waveform. But this one is a little bit better, around 3.5%. Go back to no load, and now I'm going to plug in my refrigerator. That kind of surprises me. With the refrigerator running, the distortion is actually better. If I remember correctly, I have to watch this video and see if I'm mistaken, but 1.8% is surprisingly good for a high frequency inverter like this. The low frequency ones with the big transformers, they're usually less efficient, but they have a cleaner output. That's pretty good, really. If we take a look at the waveform, nothing really to look at there. And if I can find the right screen here. Oh, there we are. And this is our draw, 138 watts. That'll come down as the refrigerator cools off. I've had it unplugged for a while, so it's kind of warm. It takes more power when it's warm. But the power factor of this one is also about 0.95, just like the other one. A nice high power factor because it is running off of a pure sine wave. And you can see that the wattage is dropping. It'll come down to the same level as the other one if I let it run for a while. So there you go, Ames Power 2000 watt power inverter. The output waveform is pretty clean. I almost forgot to mention, so what do you get for your money? This inverter costs about twice as much as the USP Tiger Claw. And like I say, you get what you pay for. When you pay a lot for crap, you get crap. This inverter is not worth the money, but it is a little bit cleaner in its output waveform, and it is quite a bit more efficient. However, it's really not worth the extra money. Anyway, I'll move on to the modified sine wave inverters now. This is the Moto Mastery Eliminator 3000 watt modified sine wave inverter. It's on with no load, and you can see that the total harmonic distortion is about 29%. 25% is as good as a modified sine can get. That's the theoretical maximum. So 29 isn't too bad. If I switch to the waveform, you can see some things that I could not see with my lesser oscilloscope that I used earlier. It kind of rings out after every transition, especially around the 0 point. I don't especially like seeing that. And these are the harmonics. You can see that none of the even ones show up. They're almost 0. The odd ones do. 3rd, 5th, 7th, etc. And let's see if they trail off in the high end. And they do. So harmonics 17 through 31 are quite low, but existing. And let's see what happens when I turn a load on. The distortion did not change much under a 1500 watt load. It'll go up slightly as my battery voltage droops, unfortunately, but there's the waveform. I do not like seeing that. It is a square wave. And you can see that the harmonic content is quite bad now. Well, that's not good at all. It is a square wave. Now, I had tested this inverter before, and it performed much better than this. I'm not exactly sure what the difference is in my test setup this time versus last time. But I'm kind of disappointed. I thought I liked this inverter before. Well, that's not what I expected. But I'll turn it back on full load. On full load, or 1500 watt load, you can see that the harmonics turn into what you would expect for a square wave, because that's basically what it is. And our distortion is up around 40%. A square wave has a distortion of around 45%, between 45 and 50%. So this is approaching that. Ugly. Alright, now I'll plug in my refrigerator and let's see what happens. So it starts up and runs the refrigerator just fine. And it's not very heavily loaded, so still looks like a standard modified sine wave. Here's our harmonic content. 27% total harmonic distortion. Here's this screen. I wanted to show that again because it does really weird things on a modified sine wave. Those sharp edges, the refrigerator doesn't like that very much, and you can see that it's quite a mess. And I also want to take a look at the power factor, because that's kind of interesting too. So it's drawing quite a bit more current right now, 170 watts, but the power factor is low. It is 0.72, and running off of a sine wave it was 0.95. And a power factor is a measure of how closely your voltage and current is in phase, but basically it just means that the refrigerator is less efficient running off of this inverter, because it is a modified sine wave. There's our, go back here. There's our current waveform. This is the current that the refrigerator is drawing. And it's really crazy because, once again, it's a modified sine wave with sharp edges. There's our harmonic content. Again, quite noisy. The refrigerator is only using this one. The rest of these are all being wasted. That's quite a bit of waste. But there you go. This is a modified sine wave. And we're getting a distortion of 25%, a little bit more. Now time for the Whistler 1600 watt inverter. Unfortunately on this one I cannot show you the refrigerator because it is incapable of powering my refrigerator. However, I will show you no load and the heater. So this is with no load, 26%, pretty similar to the other one. And that is the waveform. Once again, there is some ring out on this waveform, but it's pretty typical of a modified sine wave. Here's the harmonic content. I'll turn on the load. And this one actually seems to be performing better, surprisingly. And the heater's making all kinds of funny noises off of this thing. It has other issues, but right now we're just talking about the harmonic content. And the waveform is getting close to a square wave, but is not quite there yet. The other inverter that I had just shown, the MotoMaster 3000, that I thought was a very good inverter, was a square wave at this point already. So on this particular test, this Whistler inverter seems to be performing a little bit better. I think the discrepancy in my testing this time versus other times is that this time I'm using a single battery, more in a typical configuration that people use. Before I was testing this off of a bank of batteries, and the voltage is probably drooping down to 11 volts or so on the input of these inverters under this sort of load through these cables. And apparently the MotoMaster 3000 or Xantrex X-Power 3000 doesn't handle that very well. In any case, this gives you an idea of the comparison between sine wave and modified sine wave inverters. One thing some of you might be wondering is, well, those were the inverters, what does wall power look like? So I plugged this into my wall and I'll turn it on. Well, look at that. 2.4% harmonic distortion coming right out of my wall socket. That isn't too atypical. Usually if you're below 5% coming from the power company, they consider that acceptable. 5% is the maximum that NEMA spec allows for electric motors and such. But this happens to be my power today in my house on this circuit. It'll change, certainly, with different times of day, where you're located, what loads are running in your house, etc. But here's the waveform. You can see that it's not perfectly uniform. It looks like there's some loads on the peak and the trough of this thing, plus the rise and fall isn't perfectly symmetrical. So there's kind of some weird stuff going on there. And this is right out of my wall socket. Again, this is with no load to show that the load doesn't matter. I'll turn my load on high. So my 1500 watt heater is now running on high. No difference whatsoever. The voltage may have sagged a little bit because I'm running through some cabling, but still 2.4% distortion. That did not change. Our waveform still looks the same, as you would expect. Power company certainly has no trouble powering this 1500 watt load. And there you go, that's my wall socket. And this will conclude my test of total harmonic distortion on 2 sine wave inverters available on the market as of the time of filming. And I discovered that both of those are acceptable in terms of harmonic distortion. They seem to perform adequately well. The Ames Power one I'm not very impressed with, mainly because its price point is high enough that it really should be a better inverter than it is. If it would cost half as much, I wouldn't have a problem with it. And what I really learned today, which I was not expecting, is that this inverter that I used to like quite a bit is not quite as good as I thought it was. It still performs admirably if you give it a good high input voltage, at least 12 volts, but it doesn't seem to like low input voltages so much. And the whistler was a little bit cleaner than I was expecting. I know that it radiates pretty badly. I did not test that with the equipment I have here. I'd need different equipment for that. But regardless, it buzzes a lot when you're powering things, the output voltage isn't steady, and it refuses to start some difficult to start loads like my refrigerator. So this would be pretty much worthless to me, whereas this is still useful. In any case, that will conclude this video. Thanks for watching.